Welcome back to the Demystify Sci podcast. I'm Michael Shiloh.
I'm Anastasia.
And today on the show, we have Dr. Alexander Unzicker, who is something of a historian of physics and also a theorist himself. But ultimately, he's a physicist who has raised some really interesting questions about the fundamental understanding of the universe. And so we are going into the very large, the very small, how light and gravity work, how they're related, what they tell us about what the atoms are doing, all of our favorite topics, basically.
It was fantastic. Dr. Unzicker is super well read, has a super functional overview of history. He can explain the provenance of ideas. He can point out where things have gone awry and is so contemplative and interested in seeking out the answers to these questions that this is one of my favorite conversations that we've had for a while.
If you enjoy it, go ahead and share it with somebody, please. That is the only way we increase our audience, which is the most important factor for bringing better and better guests to this show.
You have no idea how many times I've emailed someone and they're like, call us back when you have 40,000 to 50,000 subscribers.
So help with that, please. Just share it with somebody. Maybe they'll subscribe. We want to actually grow this into something where we can grant grants and actually fund independent research that might not fit into some academic channel.
Basically, we have enough stuff that we want to do for this podcast that we would need to work on it full time. Right now, our time is split between doing this and other things in order to be able to make a living. And so the more people who support us, the more time that we can devote solely to the podcast without having to think about anything else and with the motive power to make it better.
So come over to patreon.com, join the group, get early access to all these episodes, get access to our special content and advisory capacity.
And if you're sitting around and you're like, man, I would join the Patreon if they just offered me blank, maybe reach out to us and tell us what blank is, because maybe we can give it to you and then you'll sign up.
All right, guys, enjoy this conversation. I hope that it is the first of many with Dr. Unzicker.
And a huge thank you to Dr. Unzicker. Huge thank you to Dr. Unzicker.
This has been the most chaotic intro that we've ever
good.
done.
We'll edit it.
All right, guys, we'll see you next time. Enjoy this conversation.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see in the dark.
Yeah, you mentioned that I'm in history, yes, on purpose, because I think if you want to really find out something, it's not enough to look just at the present state. You have to go to the history of physics to better understand. I'm not a historian for the very reason, but just as a method to understand how thoughts were proceeding, how ideas were developed, and to identify the mechanisms when real progress happened. That's the reason why I like history of physics.
And you can also see how ideas are built upon other ideas, and sometimes you have to go back several generations of ideas to see perhaps where there might be new insight available.
Yeah, you said something interesting where you said that you don't see yourself a historian, but you're doing a historian's work. So why the discrepancy?
I wouldn't call it like that. A historian does it for the sake of history because he wants to know how that occurred. But often, I see often historians who are not really interested in the real stuff, so to speak, in physics. So my take is that, well, let's take that example of variable speed of light and Einstein. There is a lot of history because the history is interesting, but what's really exciting is that such an idea like variable speed of light hasn't been developed in another way. So and to appreciate properly the impact of this theory, I mean, automatically you do history. I mean, there are people writing about variable speed of light. A couple of years ago, some guy from Portugal published a book, Variable Speed of Light. I am the one who discovered variable speed of light. I said, no, sorry, Einstein did it 80 years earlier.
Yeah, can you unpack that paradigm for us a little bit? Because most people are under the impression that the speed of light is constant in all reference frames.
Okay. That would be
break it down.
The first part, maybe.
Yeah.
Variable speed of light. Where to start? Again, history. It's just interesting that Einstein, when he was about to develop general relativity, his very first idea was variable speed of light, because the equivalence principle that says you cannot distinguish whether you are in a dungeon on Earth, in the Earth's gravity, or if you are in a rocket in outer space and accelerated. Okay, so in both cases, these two situations are not distinguishable. There are no experiments that can determine the difference, and so on. So Einstein went ahead and said, okay, let's consider the acceleration situation. Then some light ray, which is coming in from the side, will be curved. And accordingly, he followed. So in a gravitational field, there has also this. There has to be this bending of light waves. Okay, this is nothing new. It's just the equivalence principle. Okay, and the very first idea was that how could that bending of light occur? Well, a variable speed of light, as in the atmosphere. You have, classically, if you look at the sun at sunset, there you have this bending of light rays. So the idea was that.
You mean that they also change frequency as they go, which is slowing them? Yeah.
So he introduced a variable, an index of refraction, depending on the masses, on how close you are to a mass. And if the speed of light is lower in the vicinity of masses, you can exactly reproduce that relativistic effects. Now, I'm jumping a little bit ahead because actually, or unfortunately, Einstein in 1911 did not develop the theory in a correct manner. He just considered frequencies, but not wavelengths. And so he dismissed the theory. He gave up on that and developed the other geometric formulation. And it took until 1957 when Robert Dicke, the well-known American astrophysicist, corrected that error by Einstein and developed a proper alternative to general relativity based on variable speed of light. There's it's really equivalent. All classical tests come out the same way, and I found that very intriguing. Because
Well, it plays into the CMB at one point in your book too, which I really want to talk about. The cosmic microwave background, and also, I'm sorry, I meant the redshift. Sorry, the cosmological redshift. Because Dicke's explanation for that is not expanding universe situation.
Yeah, that's one of the key features why I think variable speed of light formulation of general relativity is so intriguing, because it gives you explanations. And maybe the most striking feature is that it explains the Hubble redshift, because in our contemporary theories, well, there is no reason from first principles why the universe should be expanding. Why should there be a redshift? We just observe it and say, oh, it might be expanding. No, you have to explain it. And what Dicke did, just continue logically what he developed with general relativity. He said there is a index of refraction dependent on masses, And of course, all masses in the universe thus contribute to that index of refraction. That means if you have an expanding, mind my words, an expanding horizon, which does not mean that materially there's expansion, but just light spreads, And if light spreads, so you see more masses into that horizon, and more masses cause the index of refraction to change over time. And so we have a cosmological evolution. That means the speed of light has to decrease over time. Okay, and this is something on top on general relativity, because general relativity, as developed by Dickey in 1957, just reproduces the spatial features and light deflection and the classical tests. But beyond that, you have that temporal evolution of the speed of light. And then,
can I just pause you for a second? I want to unpack one thing first of all.
It's
It's all really fascinating. This is one of my favorite topics.
Business, so I'm talking too much in a row.
Well,
No.
I think that we need to step back and just orient people, and honestly myself. Like, you guys are getting very deep very fast.
Yeah.
And so I just want to orient myself. So ask your question, and then let's orient again after we get the answer.
Well, I'm really curious about this model because, first of all, I'm very dissatisfied with the expansion of all things. This is very strange because space-time is really just a coordinate system, and so the expansion of locations doesn't really satisfy me. But with respect to this refraction based on gravitation, isn't refraction a chromatic effect where certain wavelengths will be preferentially affected, but the cosmological redshift is achromatic? It affects all wavelengths equally.
Yeah, it's achromatic. We're not talking about no.
So are you?
No mention of that.
I think that the reason that Shiloh asked that is because you're saying that the variable speed of light comes from a shift in the index of refraction as you integrate over distance traveled. And so I think that you're just trying to make sure that we're not actually talking about refraction.
Well, yeah, it's like a refraction that changed.
I think that it's an analogy.
It's actually,
right?
maybe it's too abstract terminology to forget about index of refraction. I mean, just the light speed decreases, and that's it. Okay, you physicists call it, but forget about index.
Can't we just call it friction?
Friction would be something that dissipates. Okay, you have just the speed of light becomes slower,
but why?
If there are masses nearby, it just slows down.
Well, okay, so that's let me
back it way up.
Back it way up. Okay. So we start with this idea of Einstein, and we started this conversation by asking about the variable speed of light. And the variable speed of light, when you generally go out into the world, is considered to be a constant. And Dr. Unzicker, what you're saying is that variable speed of light is actually part of general relativity as Einstein wrote it. And then after he wrote it, was that just a piece that was discarded as being not part of the canon?
He himself discarded it. Yeah.
I see. And why did he discard it?
Okay, that would be another sideline, but let me get to your first question. I mean, why is it generally considered a constant? You have to realize that the speed of light is always the wavelengths times the frequency, okay? Or in formulas, C equals F frequency times wavelengths lambda. So you don't notice when speed of light changes, because every yardstick you have in your hands, be it atomic clocks or lasers or whatever, they change accordingly, okay? So the change of the speed of light is something very hidden on first sight, and you can only observe it, so to speak, indirectly, okay? Because if there is a region with lower speed of light, the light will be curved towards that region, as it occurs in the light deflection at the sun. measured by Eddington in 1919. That's one of the most famous tests of general relativity. Okay, so what that was, I think, your question, and then is it equivalent?
Well, I think your question was more just why is it slower? Is that right?
No, the question was why did Einstein discard variable speed of light?
Yeah. I mean, I think it was just an error, very banal, not considering
Well, it seems like
wavelengths.
okay, so so you're saying that he didn't consider you said that he had it in his theory. So if he had it in his theory, and at some point it
Well, it forms the bedrock of special relativity, right?
It's a technicality. It's a technicality what he did wrong. I mean, the idea was correct.
Okay.
That you have a lower speed of light in the vicinity of masses. But the question is how much, okay? So, and he said, okay, this masses influence the frequency and accordingly also the speed of light. But as Dickey later pointed out correctly, it influenced not only the frequency, but also the wavelength. So in Dickey's theory, the change is twice as much as in Einstein's original idea in 1911.
And that is because if you change the speed of light and you change the wavelength, the frequency stays the same. You wouldn't notice the effect because they're in proportion to frequency.
No, if you change just the frequency, you change also the wave, change also the speed of light. But if you change both, the speed of the change in the speed of light is already more pronounced. It's even more pronounced. You know?
Yeah.
So, and that was the famous error that Einstein did. I mean, you can't blame him for that. He didn't know the correct result. So for Dickey, it was much easier to discover. But then his first attempt was later also discarded because people were saying, "Oh, you got the half of the correct deflection." Okay, so Einstein's original idea of 1911, if you do the calculations, it leads a light deflection of 0.87 arc seconds if you go close to the sun. And the eclipse result of 1919 was 1.75 arc seconds, which is the double amount. So for that reason, if you're showing that paper to people today, say, "Oh, that's wrong because he got half the value." Okay, he got that wrong, but as a matter of principle, the idea was the correct one. It just technically failed to take into account the other wavelength dependency, which was done later by Dickey.
I see. So when Einstein did his calculations, he came up, if you were to do the calculations according to how Einstein wrote them for how much of this bending of the light around the sun you would expect to see, you actually end up seeing 2 times what the theory predicts. And so is that why people stopped? So I guess I'm trying to understand the distance between Einstein and Dickey. So Eddington does this experiment. He shows that it's twice the distance that is expected. Twice the arc seconds.
Why is it celebrated as a victory at that point?
Yeah, like how do they rectify the difference between the theoretical prediction and the thing that Edison found?
Yeah, well, actually, the story is quite complicated.
Eddington, sorry, not Edison.
Quite complicated in detail. We're talking about 1911, the first idea. Then let's say Einstein did also discard it for other reasons. Okay, so and he developed a theory based on geometry, on differential geometry, and then he had another failed attempt, which made the wrong predictions. And then eventually in 1915, he came out with the correct theory, but based on that mathematical differential geometry approach, as opposed to variable speed of light. So, and that differential geometry approach got spectacularly verified 4 years later when Eddington undertook his expedition to South America and observed the solar eclipse and measured these 1.75 arc seconds. And then this 1915 theory of Einstein, these geometrical mathematical formulations, got celebrated as the new sensation, as the new gravitational theory. And all earlier attempts at this point were regarded as preliminary, wrong, not with the correct method. And what I'm saying is the variable speed of light approach was correct as a matter of principle. Instead of shifting to the geometrical formulation, he should have just fixed that problem with the light wave, as Dickey did almost 50 years later, and everything would have been fine. Okay?
I see. Okay, hold on. Before we move on from this point, hold on. That's what I'm trying to. So when he has it written and it is just looking at, you said it was looking at just wavelength and not frequency? Or the other way around?
Einstein was looking just at frequency, not wave.
So he's just looking at frequency, and the key point of why he started looking for the differential geometry was because it didn't line up to observations. And so
not yet. There were still other reasons. There were still other reasons anyway.
I see. Yeah. Okay. So there was basically just like there was motivation for him to feel like the mathematical approach with just frequency was not enough, and so you had to find some other way. And so he left behind this frequency wavelength relationship to light and started looking at differential geometry of what? Do you understand this?
Space-time.
Different.
Yeah, let's make a simple example. Not to get too technical. What's differential geometry? It's if you live in a curved space. That's still too complicated. A curved surface. Imagine a curved surface like the surface of the Earth. Okay. It's curved in the sense that triangles do not have the angular sum of 180 degrees. Or if you, there are no true parallels, okay? Because if you go a straight line would be a geodesic, like the equator, which is the maximum circumference of. If you just go on a meridian, it's not really a straight line. So in this curved space, you cannot really draw a proper rectangle. Okay, so everything is curved, everything is messed up a little bit. Well, actually, space-time is messed up in this way, and there are two ways to mathematically fix that. Either you develop this fairly difficult, complicated system of differential geometry with metrics, how to measure distances. Already on Earth, if you compute the distance from London to New York, it's not that easy. If you just, it's not as easy as in the plane. You develop that system of how to measure distances, how to transport vectors, how to set up curvature tensors, and so on and so on. This is one thing, but you can also describe the same physical reality and saying, okay, we live in a flat space. Everything is Euclidean. You have very easy calculating of distances, Pythagorean theorem, very easy. But your speed of light is variable. And so the point is, look at the map. If you want to go from, you're living at the West Coast, right? You want to go to New York, and you can go a straight line, but that's not the fastest way. The fastest way would be obviously to take some highway because the speed there is faster. Okay. So the faster speed in that region causes your path to be curved. That's variable speed of light. You just light just searches for the fastest way to connect the point A to point B.
Yeah, so along those lines, why was he off by a factor of 2 in the first place? It just seems like such an extraordinarily simple factor.
Yeah, but it is simple. I mean, you know this. Imagine this formula. Is it okay for your audience? I mean,
yeah.
You know, it's a podcast, but I mean, speed meters per second equals meters times 1/2, the frequency. Wavelengths times frequency. Yeah. So we have this very simple formula, and you imagine that. The wavelength are increasing by a factor. The frequency is increasing by a factor. And so the speed of light, being the product of these two factors, has to increase, by the square of this factor, technically. But since we're talking about very, very small changes, so that would be just the double amount. Okay, let's translate that still in easier language. The speed of light increases by 1%. The wavelength increases by 1%. The frequency increases by 1%. So the speed of light increases by 2%, more or less. 2 comma something negligible. That's factor 2.
Okay.
He just forgot to take into consideration the wavelength.
So I guess it just cracks up in the question of why this is happening. Like, why is the speed of light changing in these gravitational systems? Because if it's analogous to refraction, I think this is what Anastasia was getting at earlier, is that the atomic relay process of getting a piece of, an action of light from one side of a pond to the bottom of the pond must involve all sorts of relays. And you can think about this as the photon losing energy as it travels through the medium. Yeah. And this is generally how I think about refraction. I'm not sure if most people think about it that way, but I think so. Yeah. Is something similar happening in the gravitational situation? What are the additional pressures that are causing it to lose energy?
Yeah. Okay. Yeah. Let's look at it from that way. Dicke developed it very nicely, and we're talking about what happens to light when it's traveling, and there are two situations. The first is, imagine there is no temporal variation, just spatial variation of the frequency of the speed of light, and you have the situation as in glass, as in water. Okay, the frequency does not change, but the wavelength must change. So we observe this curved light. This is well known. The other extreme is you have no spatial variation, but you have just temporal variation. So you imagine a photon light from a distant galaxy traveling more or less through a homogeneous universe. Okay, and then Dicke said it's quite easy to technically figure that out. What happens is the wavelength must stay the same, and all the change of the speed of light goes into the frequency. Okay, what does that mean? That distant light arriving from distant galaxies does not change its wavelengths, but we on Earth, observing for billions of years, have that change of the speed of light that involves wavelengths and frequencies. So we are living here in a world where wavelengths and atoms are continuously shrinking. Okay, so if we observe light from the very distant past, which is emitted by the same atom, we observe it has preserved its wavelengths, and with respect to our today's wavelengths, it's longer, and that's the redshift. So this is
What is this idea of us shrinking, though? This is
key.
interesting.
No, this is key, because this is the explanation that there has to be a Hubble redshift if you describe gravity by that variable speed of light. No? So we're coming back to the earlier argument now, and one aspect is that you reproduce all the general relativity stuff, all these tests. But the other really nice feature is if you just continue thinking logically, applying the same formulas, you see that over the course of history in the universe, the evolution of the universe, the speed of light must decrease, and necessarily you observe a redshift. Okay.
And this is assuming that the universe had a beginning or something? You're assuming that the universe progresses.
It has a beginning.
I see.
It has a beginning. You might call that big splash, maybe, because light obviously spreads. There's no way for light not to spread. It necessarily spreads, but not the material. Okay. All the material, and that's what Dicke said in 1957, all the matter is basically at rest, apart from little local disturbations, but all the matter is at rest. And this is the huge difference between the conventional theory and Dicke's cosmological formulation of variable speed of light, that it gives you an explanation, so to speak, of that strange phenomenon of the Hubble redshift.
Mm. You said something about our rulers here on Earth shrinking or something like that. Can you explain that a little bit?
Yeah, it's just a consequence of you have to assume that the speed of light is influenced by masses. Okay, obviously, the more masses there are around, the smaller your speed of light becomes, and the closer these masses are, also the smaller the speed of light. But what influences, maybe an additional hypothesis if you want, what influences your local speed of light is all the visible universe, all the horizon, all the masses in there. Of course, since maybe we call it the beginning of the universe, that big splash, some 30 billion years ago. Okay, so you have this huge amount of masses contributing and constantly lowering the speed of light. But I mean, the universe becomes, each day, it becomes one light day bigger. Okay, you have this increasing horizon, you have an increasing amount of masses in this visible horizon, and then that causes your speed of light to decrease.
Wait, do you understand why the horizon is expanding? Do you?
I am like 10 minutes ago still.
Okay.
So
I'm still trying to figure out why the horizon is expanding.
Still too technically. I mean,
it's not. Hold on, it's not too technical. Can I ask my math question really quick?
Yeah, but as long as we get back to the expanding horizon, okay. I'll make a note. Yeah.
All right, you said something that I have just been sitting here thinking about. So you basically said that the speed of light is meters times 1/2, which is wavelength times frequency. And you said something, which is that if you double one, if you increase each by 1%, or you decrease, let's say you decrease each by 1%, that you would get a doubling of the velocity.
No, it slows down.
No, I decrease it by 1%, which means I multiply it by 0.99.
Yeah.
And so the frequency 0.99 times the wavelength 0.99 gives approximately a 0.98.
Right. So shouldn't that be the same velocity? I see. Okay. You are, yes. Okay, that makes perfect sense. Okay.
All right, let's go back to this expanding horizon thing.
Yeah, it's not bad that if you have some redundancy here, I think it's fine. Yeah,
Well, if we don't understand it, somebody else probably doesn't understand
from there, because
no, it's good. This is how we figure it out.
Yeah.
Thank you. Yeah, no, it's good because if we miss something, other people probably miss it too. So it's good to restate it. I like the idea that gravity and light. I mean, obviously, anybody who studies physics long enough starts to understand how similar gravity and light behave. I mean, of course, they both follow this inverse square relation, and it's hard to not see one interacting with the other. But I really want to understand this expanding horizon thing, because I think I almost do, in that light is a radial projection, and I think that it's related to this idea.
Light is what?
It's a radial projection, right? It thins out with an inverse square as if it's radial projections, essentially. Like if you have four rays taking up
the power radiates. I mean, if you double the distance from the sun, we get 1/4 of the power. Yeah, radiated power. Yeah, you could call that the same law, like gravitation. I would say that for light, that it's quite obvious. For gravitation, it's still a little bit mysterious.
Yeah, well, we have some ideas. We've talked to some people who have some ideas, but we can get back to that later. Is that related to your explanation for this thinning horizon, or this expanding horizon? Can you unpack that? Why is the horizon expanding? I thought it was related to that power function.
No, this is nothing new, nothing extraordinary. I mean, just imagine that you have empty space and there is light coming from, I don't know,
some atom somewhere, hopefully.
Yeah, some source of light. Yeah, a light bulb. Yeah, Edison.
Far away Edison, alien Edison on the other side of the universe.
You turn on that light, and that light radiates out in space.
Yeah,
okay, with the velocity of light. So what you see illuminated is constantly increasing. It's an expanding sphere, and you can't stop light from expanding. Okay. Yeah,
until it reaches the end of the
as simple as that. So the expanding horizon, in the sense that what is visible, is almost a tautology, because I mean light spreads in all directions. There is no preferred direction. So you have this expansion of visibility. You might call it visibility.
Okay.
Or also call it big splash or whatever. What I'm saying here on what's different here, the key difference is we don't need a material expansion. We don't need to postulate these receding galaxies or these expanding space or whatever. That's the difference. Just galaxies are just sitting around and continue to be there, but they're not moving. Okay.
So in that sense, as these waves spread out from Edison alien on the other side of the universe, they are going through some system of relays. They're interacting with matter as they travel across the universe, right? Mm-hmm. And you're saying that the light waves slow down as they interact with matter, essentially. And
yes. Not interaction in a general, not that they hit matter, but they're influenced by the presence of matter. How exactly that occurs, I can tell you. And that would be, let's say still some missing fundamental property one has to find out. Yeah.
How do you know that they're not interacting with matter? Because certainly a lot of people have tried to make that case.
We're on the same page.
No, light interacts with matter.
But how do you know that that's not slowing the light?
Yeah, because if something is like more or less
there was a misunderstanding, I guess. I just said that there is nothing extraordinary here. Okay, light spreads, and when it hits the planet, it doesn't go through the planet. It's just stopped by the planet. But if it goes
through a neutral gas or something, it will just be relayed, right?
Even if it goes through empty space, let's say in the vicinity of a galaxy or a star like the sun, I almost hit it, but not quite. I just go around, okay? But the light will feel the region with smaller velocity. So it will be curved.
So
in this sense, it interacts.
right, and that's the thing where you say empty space, and I have a really hard time imagining that there's actually such a thing as empty space. There might be rarefied space.
Or just neutral atoms that aren't interacting classically with it.
Yeah, like, so because, again, this is out of my depth, so forgive me if this is nonsensical, but
No.
Isn't
It's absolutely justified what you're saying.
isn't the energy of the vacuum energy justification that there's something in empty space?
Yeah, okay. I mean, technically, it can be empty, avoid if you have no atoms in there. I mean, the average density in intergalactic space is something like 1 atom per cubic meter. So very small, but still something. There is a density. But technically, you can imagine that it's really empty, not even an atom. However, you're justifiably, you say, is that possible? What means empty space? What does space consist of, even if it's empty? And people have called it, well, vacuum fluctuations in, let's say, in the current fashion. But of course, there has to be something that influences, because in our mind, philosophically, empty would mean there is no possibilities that something interacts. And we need that interaction because I said the speed of light is influenced by the presence of masses. How does that influence of the masses arrive at the light? Yeah, I don't know.
Yeah, that's what we're playing with, I guess.
And I think that this is a philosophical break that you come to a lot in these discussions, where at this point you have to ask, if there's something detectable, that means that there's something that is being detected. And you can go in the Tegmark direction and say, no, it's just the detection.
It's just the laws of nature are being warped.
I think that the mathematical universe is the fact that there just is math there,
right,
and the math can be detected. And that's a philosophical, that is an ontological, philosophical, epistemic, whatever you want to call it. That's a belief system. And you can stop there and you can say, I believe in this, or you can stop there and say, that doesn't make sense. That's not possible.
Yeah, I guess the question is, do you have hope that somebody will mechanistically explain the effects of gravitation in this way?
Yeah, unfortunately, there are a lot of avenues we could go from there. You mentioned Tegmark, the universe, and so well, actually, I have written about the mathematical universe, book entitled like sounds a little bit like Tegmark's, but it's not really the same stuff. There's, let's say, very little overlap. Anyhow, the thing to mention here, I guess, is Mach's principle, which is the idea that where does gravity come from? It comes from the distant masses of the universe. And this is very profound, because he was after the very reason of gravitation. Okay? So the idea is, obviously, the presence of masses do influence inertia. You cannot define inertia without the presence of masses. And Mach, and we are talking of 18-something, deduced that gravity has its reason in the presence of the distant masses in the universe. And so you call this a philosophical approach, but it translates into very concrete physics if you think about that variable speed of light theory of Dicke, who referred to Ernst Mach, by the way. So because in that formula, if you say, okay, the speed of light is influenced by the distant masses, you have all the masses of the universe. And by considering the spatial gradients and the spatial change, you get gravity. So gravity is a consequence of spatially variable speed of light. Spatially variable speed of light has its origin in all the masses in the universe. So this idea is a technical formulation of that very old idea by Ernst Mach. And Mach had no chance to see that because there was no cosmology at the time. So guess how excited he would have been if Mach would have been able to know about the size of the universe. Or even Einstein. Einstein didn't even know about the size of the universe in 1915. Yeah? That's why I occasionally like to go back to history and say, look at this. They couldn't know about. If they had known, maybe history of physics would have took another course.
Well, yeah, Mach is incredible. He wrote a big book on mechanics as well. And I always, my background, my PhD is in material science, so I always think about these things in those terms. And I always thought of Mach's principle as essentially saying that we're connected to all of the bodies that are surrounding us, essentially. And of course, their influence depends on their distance, which must reflect something about the tensile interactions between us and those distant bodies. And it makes sense if you start thinking about gravity as a tensile process that the speed of some sort of deformation of it would also be dependent on the location of those bodies as well.
The speed of deformation, what do you mean by that?
Well, if you're talking about
you got to go back to explain that light. You're talking about light as a deformation.
Yeah. Well, I would see if there is a substance which connects these bodies to one another and light is an interaction between those two substances, it must occur within the same medium that's responsible for gravity. And so it is essentially, in material science terms, it's a deformation of that material. And the deformation has a characteristic speed.
It's very interesting, this deformation of the, and you can think about, you can also think about electrodynamics in these ether terms, and it's very related to deformation.
But the speed I guess the speed makes sense to me at that point too, because I would also expect the speed of like a guitar string, right? If I tighten it, it's going to be a different vibration than if I loosen it, and that's going to depend on how loaded the system is at any given point.
No, I mean, we can go to that topic later. It's very interesting also ether in electrodynamics, but maybe we stay a little bit with Mach and the fundamental of the essence of the fabric of space-time. So, well, in first place, it's not known. You can't tell. There is no fundamental theory behind. There's one feature of this variable speed of light that I explained that it realizes Mach's principle, and if it gives at least a technical formulation of how these distant masses are related to the speed of light and to the gravitational constants, then we have achieved something very big, because we have a relation between the gravitational constant, the speed of light, and the mass and the radius of the universe. And this is huge, again, because a lot of people have thought about that relation. So, well, in very simple terms, if you analyze the gravitational constant, it has units, okay? Has a kind of strange units. It's meters, cubic meters over second squares, kilograms, okay? So
I like that everyone just takes that for granted as being the case. Like, I remember in physics learning this and the teacher being like, yeah, the units don't make sense. Don't worry about it.
Well, they actually can, they can make sense. Yeah, they make sense.
Yeah, I mean, if you take Newton's law say you have a force, Newton, and this force is one mass times the other mass divided by the square of the distance and times this mysterious gravitational constant. So we have a force on the one hand side, Newton, and on the other hand, kilograms squared for the two masses divided by meters squared for the distance squared. So just to bring that together, okay, just to fix that, it's there's no way other than taking this as cubic meters divided second squared and kilograms. So
I guess more that what I want to say is that like if you're looking at a simple like meters per second, there's an intuitive sense of it being a quantity that you are familiar with and you can feel. And I feel like with something like with the gravitational constant and with Newton's, it's not as intuitive of an experience. And so you read the equation,
I love this comment. You know why? because I always wondered, I mean, how can I imagine that? That's very strange. And I remember being in high school and freaking out about this strange unit, cubic meter. What's that? Is that a acceleration of a river taking away cubic meters of water, depending on the mass of what? Or just generating stupid ideas about that. But that's that's a little bit how science works with this. And I'm convinced that the first one who developed this formula, it was Erwin Schrödinger in 1925. I think he more or less thought about this constant and said, okay, look, we already have cubic meters divided by second squared. Okay, let's take out square meters and square seconds. That would be a c squared, the square of the speed of light. Okay, that would be already a part of the explanation. If you see that c squared written into the gravitational constant, okay. So what remains is meters meters divided by kilograms, which is a distance divided by mass. And actually, it turns out that if you put the numbers in, and if you compare the numbers, you put the radius of the universe in meters, and you put the mass of the universe in kilograms, and you are there. That's the same order of magnitude. And that's spectacular. This is huge. It's an incredible coincidence.
You can also factor out the rest mass of a hydrogen pretty evenly as well. I think you end up with the rest mass over 2 or something like that as well. But
is that a case of significance, or is that a case of
that's still another coincidence? That's still another coincidence. That's still
interesting one.
Numbers, which are related. But this would be the first step. And historically, it was the first idea. There are I dig it a little bit in the history and found out that there are hints that Einstein, in his conversation with Alexander Moskovsky, was one of his biographers, already arrived at that, but he could not really compare it because he didn't know about the size of the universe in 1915, in 1920. Nobody had discovered that. And only in 1923, when Edwin Hubble then said, okay, look, there are galaxies out there. So the universe is hundreds and 1,000 times bigger than we thought before. Then Schrödinger came up and said, okay, that could be the coincidence. It could be that Mach was right, that the value of the gravitational constants is actually related to the speed of light and the masses and the distances in the universe.
When you say the size of the universe, do you mean the observable universe?
The observable universe, that distance that since the Big Bang, or let's call it Big Splash, light was traveling.
Okay, again, stupid question. How are we sure that that's as far as we can see?
What?
Well, like there's a
No, it's not a stupid question. It's about determining distances. And okay, what you observe is the Hubble redshift. That is, you see redshifted light. That's not easy. That's not difficult because you just see certain patterns. You can identify, say, some hydrogen line or in distant galaxies, very redshifted by a factor of even 10 nowadays. And then you have to determine the distance, which is the difficult part. but it's doable. But anyway, maybe we're not going into details how to determine distances, or we can. But at the very end, you need a distance and you need a redshift, and then you have you can translate this. Classically, people translated that redshift into a receding velocity. Okay, and then you had something like
by assuming it's a Doppler-like situation.
Yeah, assuming it more or less it's a Doppler, and then you have a measurement of velocity, which is, I'm always going to the units, which is meters per second. Okay, and you have a distance, which is meters, and then you divide meters by meters per second, then you get a time. Okay, the time needed to do that expansion, and that's basically the age of the universe.
How does that change if redshift isn't a Doppler effect and is instead some inherent property of transit? Does it change?
It technically it does change a little bit, but it's a technicality. If you're talking about orders of magnitude, we're still in the billions of light years. If you do all the math and consider all the dependencies and consider all these change in wavelengths, you get something like, let me think. You get half of the usual. I hope I'm not mistaken. No. You get half of the usual radius, but instead of 1.3. 10 to the 26 meters, so it would be just 6.2 times 10 to the 25th meters. Yeah, it's not very important, but I mean the key thing is that since Hubble, whether you call it expansion or whether you calculate it with this variable speed of light theory, the universe has a beginning. Okay, there's no doubt about that. The universe has an evolution. You see that. It's not a steady state model. People were discussing this in the 60s. But you can determine a beginning. And then accordingly, you have also range of visibility, a visible horizon.
Yeah, because I'm not seeing a beginning here. I'm just seeing that if radiations are... like if your experience of these radiations is dependent on distance just because it's a radial function, and gravity is also obeying this radial function, then it makes sense that the influences would be proportional.
You would also imagine that as you traveled around and stood in different places in the universe, that you would see an equivalent radiation in all directions from any point that you stand, which implies a strange universal beginning all at once from all locations. Right, because like so right now you're standing at the center of the universe and you look out 13.8 billion years in all directions, but if you move 10 billion years over, you're probably still going to see 13.8 billion years in all directions.
Yes,
right?
We're not in a special place here. Yes, you're correct. You're right. What you still need to postulate that at the moment of this big splash that occurred everywhere in the universe at the same time. You might call that strange, but well, at this point, my line of defense here, the conventional model is strange. So they don't have a better explanation either. So,
well, so I think that what Shiloh's trying to get at is he's like, well, that could just be an artifact of the act of observing, where it seems like everything is beginning from everywhere all at once, but in reality, it's just that you can only see so far from each place, and it's always been there. And so as you move, you're still gonna see this. You're just gonna move your frame with you, and there's not a place where it began. It's just the record of perception that begins.
Yes, I guess I agree.
Okay.
Yeah.
I see.
Interesting.
Wow. Okay. So, one thing that you talk about also in this book. What is the book's title? ELK, Einstein
Lost key, Einstein's lost key.
Einstein's
How he
lost key,
overlooked
yeah.
the best idea of the 20th century. Yeah.
Yeah,
Yeah,
which
a
is,
little bit publicizing. Yeah, you have to.
yeah, check it out. We'll put a link to it in the description.
I mean, everyone abuses Einstein, okay? I took the liberty also to use it for at least something he did, okay? People are abusing him as a crown witness for dark energy or whatever stuff here and predict this. Not even his prediction of a gravitational wave was very, you can trace back very cleanly to Einstein. But this idea, at least, you can trace back.
Yeah, no, I appreciate it. You're actually very reverent of Einstein, and I really enjoyed actually that treatment because generally when people love to kick Einstein as much as they love to worship him, and but I did want to.
That's very strange. Yeah, we could open a sideline about that if you like. But not necessary. Yeah.
Yeah, well, it's kind of the same with any rock stars or big movie stars. We love it. We love them, but we love them to make mistakes. Also, it's kind of makes them human to us somehow. These gods almost. But
yeah, it's kind of strange because I mean he's worshipped as the hero and. Literally everything people link to him, the string theorists claim that their fantasies are related to Einstein because our 26 dimensions are more than usual dimensions, and Einstein in one occasion considered a fifth dimension. No other relation so far. Or people are claiming that Einstein predicted gravitational waves. Finally, Einstein verified. It's not that easy. I think that he's very often used to justify this big projects, this high-tech physics. And on the contrary, he was someone sometimes even disinterested in experiment. Not always, yeah, but he was usually a very intuitive thinker, and the key idea he had for general relativity was what we call a Gedankenexperiment, a thought experiment. Okay, let's assume that we are in a dungeon on Earth or in outer space. So the key ideas he derived from basic principles, and he was after the big fundamental questions. I mean, how does it work? How can I explain gravity? How can I calculate the mass of the proton, of the electron? That was the kind of question he was after. And for that attitude, I admire him because he honestly looked for very basic laws of nature, and he was a lifelong searcher for the truth in that sense. Yeah.
And you have a whole chapter on the importance of intuition in basic physics discovery, and I think that's really important to remember because so often popularizers of quantum theory or of different strange aspects of astrophysics, they'll tell you that your intuition shouldn't be trusted and that intuition will get you in trouble. Feynman is famous for this kind of thing. And it seems like that's not really consistent with the way that people have thought in the past at all, actually.
Yeah, I agree. Yeah, Feynman is a little bit of an antipode of Einstein. As much as you can like Feynman, he's very funny. But in that sense, he argued that kind of shut up and calculate style of doing physics, and it just comes out right. It's fine. It's a model. We can explain it. We have the experiments that agree. No problem. But it's a little bit superficial because, sometimes. I admit that sometimes philosophy does not bring you ahead. There has been some philosophical texts which are not really useful for physics. But on the other hand, all the big advances, all the real progresses, revolutions in physics, they came out of that philosophical quest for the laws of nature. And that's.
Yeah, I was reading another interesting paper that one of our patrons, Steve, suggested just like, I'm going to mess up the name, but I think it's...
Something's wrong in the state of quantum electrodynamics.
Yeah, have you read this paper?
Yeah, of course. I have made a video about that. Oliver Conza. Yeah, he's really, he did a brilliant historical study about about quantum electrodynamics, and showed. I don't want to spoil the video.
Oh no, please do.
He showed that there is.
We'll link the video too.
It's a mess. It's a mess. It's a mess. Yeah.
Well, what's interesting is
may I suggest that one line we could go ahead discussing is that because we arrived at the gravitational constant before, and I said this is a big accomplishment of that variable speed of light developed by Dickey, that he's able to explain the numerical value of the gravitational constant. Okay, there is a reasonable equation, g equals speed of light squared, and so on. Yeah, and this is an indicator of revolutions in physics, because if you look, I should start maybe from another perspective. Still, I mean, what do you think where the gravitational constant comes from? That's 6.67 times 10 to the minus 11th. Is it known?
You're asking me where I think that it comes from?
Yeah.
I mean, I can tear it apart in terms of the tension that's being applied to, like, I start with the idea that mass reflects some tensile process that's occurring between atoms. And if I essentially take Prout's law, which is that atoms are essentially assemblages of hydrogens, then I can make a tensile web that's reflective, from which the gravitational constant falls out when you have these pulling bodies, essentially.
Yeah, it's fine. So you're already developing, let's say, in an intuitive manner, Einstein style ideas. I mean, how to explain, how to find a mechanism, but you're seeking explanations. The majority of contemporary physicists, they just take it at face value. So it's that value and that's it. We don't have to worry about. Discussion closed. No, you have to explain. Why is it that number and why it's not double the number or 10 times the value? Okay? It's a message of nature we have to deal with. We have to explain.
Yeah, it has clues, right? They're like pieces of evidence on the table, and now the jury has to, or at least somebody has to make up a theory for what causes the evidence to be interrelated in this way.
Yeah. And I call these constants gods of modernity because the people do not question any longer these values. And that's where the history again comes in. History tells you that whenever people explained constants of nature, important constants of nature, that was a huge revolution. Like electrodynamics, the discovery of electromagnetic waves. Okay, Heinrich Hertz in 1886 discovered that the speed of electromagnetic wave is the speed of light. Wow! Light is an electromagnetic wave. We have unified optics and electrodynamics.
That's been a good day.
Revolution that influenced our civilization. No smartphones, whatever, possible without that. Okay? But it boils down to a very simple formula. It says, okay, c squared, speed of light squared, is 1 over the electric and magnetic constants, epsilon naught and mu naught. And this is this elimination of constants, this kind of simplification is, the key. These are the key insights of physics. And I can give you other examples, but I just want to,
they're valuable because they can point us in the direction of mechanistic understanding at the end of the day.
I think
Yeah.
even more than that, I think they're valuable because they're intuitive, and intuition can be trained by mathematics. Like, the Monty Hall problem, right? Where it's like you have 3 doors, the guy shows you 1 door, and then you have to choose, are you going to switch your choice or not? And the correct answer is mathematically not intuitive until you learn to think about it a specific way, and then you know if you should switch or not. And I feel like that's the benefit of simplification when it comes to mathematics, is because if you have this tiny little thing that you can kind of fold into your pocket and like go out into the woods and think about it, that's a very different experience than if you have to carry a tome of equations that's this thick in order to be able to make any kind of movement forward. You never internalize it in the same way. And that kind of simplification, I think, is out of style. People want science to be hard and complicated and like very, very esoterically
Well, it's funny because
difficult.
if you read Newton's original writing, when he describes his force laws, his basic laws of motion, they're like these huge paragraphs, right? Just to say like a force is a push or a pull. He uses all this language, right? It's not just this simple little F equals ma business that we end up with today.
Yeah.
And the same for Maxwell, by the way. It took, I
Didn't he
believe
have
it
like
was
50 equations at the beginning?
yeah, Heavisides made the ones that we think of.
I mean, that's a huge accomplishment. We almost cannot appreciate this today, what Newton did, because I mean, he had to develop all these concepts. What is mass? I mean, what is velocity? What is momentum? And it's a important piece of work. We nowadays, we are so used to all this. It's very, everyone knows what momentum is, or at least what velocity is. But he had to invent all this stuff, and this is maybe his greatest accomplishment. I mean, he has several accomplishments on also the mathematics of the ellipse and so on. But I think this is maybe the most underestimated. Yeah. And Newton said also, simplicity is the basis of things. You need to simplify it. There is no reasonable law of nature which is complicated. Yeah. And that's the kind of simplicity I argue we must search, because whenever you simplify physics in the sense that you explain something which was unexplained so far, then you have made big progress. Yeah. And electrodynamics, or this velocity of light related to electrodynamics, was a big progress. And so another big progress could possibly be a complete theory that realizes that dependency of the gravitational constant.
Yeah, that's fertile ground. I think I want to develop that more than now that you've got me thinking about it, and be able to. I have a hard time articulating it, but I've definitely played with the constants before and made some physical sense of it. So you don't want to talk about this paper. You say you have a video on it already, but
Can we define quantum electrodynamics for me?
Sure.
Can we get a definition of quantum electrodynamics? Because I've been throwing that term around a lot, but I'm not sure.
Okay. Well, completely different, but no problem. Well,
because I want to deal with I want to talk about renormalization at least briefly. It's come up enough times that we.
You didn't want me to criticize. If I care about
No, it's okay. I think it's interesting. I want to try on some ideas. So I'm curious what you think. But yeah, can you just tell us really quickly what exactly QED is?
Yeah, I mean, the idea is that I start referring to positive things. Okay, so the idea is that you have vacuum is not nothing; it is polarizable, and the idea is that light and electron-positron pairs are very closely interrelated. That means that if you have a very strong light wave, that means in intensity, okay? That means you have huge electric fields. That means a positive charge would be pulled down or pulled up. Then if you have this huge field, then space-time may eventually rip apart and form electron-positron pairs. Okay, and so far, it's a nice idea. And Feynman also developed the notion of an electron traveling backwards in time is a positron. Okay, that's again a little bit hard to visualize in a podcast because all you need is a little diagram. But
you just spin it backwards.
Yeah, I mean, there are two. If an electron travels in time and then it turns backward, okay, you have two trajectories that end in one point, and that would be pair annihilation, forming a photon. And then it travels back, and then it travels forth again, and then that point would form a bifurcation out of nothing, or out of a photon, so to speak. An electron-positron pair forms. So anyway, there are lots of details, and this would be the simplest Feynman diagram. And then you can calculate probabilities and so on and so on. The claim is that it resolves one big problem known since, I don't know, 1930 or something. And it doesn't resolve the problem at the very end. Okay. Let's say that. What's the problem? We have three basic laws, all verified, no doubt about their validity in physics, and they simply contradict if you put them together. Okay, so one thing you take is Coulomb's law of the electric field, which is analogous to the Newton's law of gravitation, the same geometry. The electric fields, if you double the distance, it becomes 1/4. Okay, but we're talking about electric charges instead of masses. So we have this Coulomb's law. Electric field is Q, the charge, divided by 4p epsilon naught r squared. That's fine. No doubt that this formula is correct. The other thing you have is the energy content of the electric field. No reasonable doubt that this is the electric field squared times 1/2 epsilon naught. Okay, so again, in simple terms, you double the amount of the electric field, the energy content becomes 4-fold. Now look at the simplest possible electric field, that of an electron. Okay, radially symmetric, and it contains energy. Just the field of the electron contains energy, and you try to calculate all the energy that is contained in that field of that one single electron. Okay, most simple particle in the universe. And it turns out the result is infinity. Yeah, something must be wrong, because we know it's not infinity, because it translates to, that would be the third well-established formula, energy, E equals mc squared, Einstein's formula. Infinite energy would translate into infinite mass, and that's not possible, because we know that the electron is just 9.11 times 10 to the minus 31 kilograms. Okay, it's very, very tiny. It's not infinity. So something is very, very wrong here. Okay. Yeah, and
but they have a way out. There's a way out.
They have an excuse.
A few different excuses. I guess.
They have an excuse, and this
okay.
They say, okay, this is infinite, so there must be an infinite mass, but let's assume that there is a negatively infinite naked, whatever that means, mass of the electron. We have to subtract from that infinitive mass, and infinity minus infinity, voila, we arrive at the known mass of the electron. I ask you, is this a theory, or is it just a cheap excuse?
Or is it just complicating things too? Like it seems like it's just leading us into.
Yeah, like why is it not? Are you saying that it could be done away with?
Yeah, well, maybe the theory is just not the best way of looking at the phenomena at that point.
What is the specific phenomena? The is it the electron? Like what is it trying to explain?
Okay, I started saying that cannot work. Yeah, sorry, I didn't want to interrupt you. You want to know about the phenomenology. Yeah, so but we have this. We have this situation that around 1930, no solution to this problem. Wolfgang Pauli said, who got the Nobel in 1945, he said, we will be regarded as the generation of physicists that failed to solve such fundamental issues like the infinite self-energy of the electron. No way out. So, what's renormalization? As I said, instead of a reasonable person would do that, something is wrong if you encounter that contradiction. Either the first or the second or the third law is wrong. I would guess that the energy content is maybe the thing to be attacked, but or a point-like electron. Maybe the electron is not point-like, but nobody has a better theory until now. Okay, make up a theory of a not point-like electron with an appropriate distribution of the field, and you're fine. You're done. Just integrate it in a different manner. If you get the correct rest mass, you get a Nobel Prize. Justifiable.
Yeah, we should get to work on that. Yeah.
Well,
makes sense to me intuitively.
we'll talk off camera. We need a mathematician. So.
Yeah, right.
Yeah.
Because intuitively, it makes sense to me. I mean, the chemists understand the electron as essentially the surface of the atom, and if that is in some way, like I keep going on about, somehow related to, like if the electron being the surface of the atom is actually the medium itself, which is connecting the atoms to one another, then it's not a problem.
But of course, that's much too big. Yeah, I mean, we have the nucleus 10 to the minus 15 meters and the atom 10 to the minus 10. And of course, I mean, the orbit, the inner orbit, but that's something we understand pretty well. I would say atomic physics. Bohr's radius at 5.29 10 to the minus 11 meters radius. And that's what chemists would call the surface of the atom. But it just, I mean...
Well, they're kind of ignoring...
these orbits, fairly huge orbits of electrons, if we might look at particles for a moment. But
well, if you look at
the size of an electron, okay?
Well, what's weird about the size of an electron is, or at least the location of where you measure that surface at. If you do the radial distribution function for the electron, you find that there is some tiny probability of finding that surface at extraordinary distances. Actually, another infinity appears.
Yes.
And so it's not unreasonable that some tiny piece of that electron is far away.
Yeah, I mean, of course, you have all these orbitals of the hydrogen atom, and these are with particular forms and stuff like that. But if you... This is all created by the motion of the electron, or let's better phrase it, by these wave patterns. The orbitals are pretty good understood by wave patterns that form, and we have this problem, of course. Conceptual problem of quantum mechanics: is it a particle? Is it a wave? And if you look at it as a wave, it seems quite huge. But if you make experiments with point-like particle, if you accelerate electrons at a very high velocity, and that's the folks of particle physics that did really their best at accelerating these electrons, but there was no hint whatsoever that it would deviate from a point-like particle. That's the problem. Okay.
I mean, yeah, that seems to be the issue, is that they're treating an activity, an event, which is an electron. It has some dynamic properties to it, and they're treating that like it's a body all of a sudden. But then you're moving an idea around, and you get really confused about what's happening.
Yeah. Okay. Now that's all. It's all valid. What I'm saying is, if you have a contradiction, either you doubt the first law or the second one, or some basic assumption. Maybe something else is wrong. Maybe our idea of a particle, of the electron, is fundamentally flawed. We have to come up with a better model. But at least then develop your model, calculate, and arrive with that number of the electron mass, which is well known.
Yeah.
Physicists cannot explain it. Okay.
Okay. So I
Now
have
they
I
come
have
up with
I
the
have a
excuse.
I have
Yeah.
I have a thought. So
Mhm.
if the
Yep.
electron is an event that is locally predominant, but it is a product of an interconnection between all atoms, right? So if we go all the way back
Like
to this,
Mach.
like Mach, right? So all of the entire universe is connected to one another. The electron is a resonant event in that network. And so two things at once are true. It contains the infinity, and yet it has a local effect that is not the infinity. And so it's
Yeah.
possible to reimagine it from that standpoint, where the math is actually, because everything that's upstream of the math is sound, the math also is sound, but what you're getting is you're getting these multiple levels of like a multi-layered view on the phenomenon at the same time.
Yeah, again, you're asking the right question. We don't have a fundamental theory of elementary particles. We just don't have it. We don't know it. This is the I would say basic conceptual problem of quantum mechanics, even earlier than quantum electrodynamics. We're talking about quantum mechanics. Is it a wave or is it a particle? And there were endless discussions and thoughts and interesting ideas. I favor the Broglie's ideas on that, but we're not there. We're simply not there. So I think the problem is ill posed in the sense that there is something before we make the wrong assumptions, which then in turn leads us to talk about particles and waves, but we might be using already the wrong concepts. Okay, so I'm now heading towards my fundamental ideas about space-time, but you wanted me to debunk quantum electrodynamics, and
we didn't have to debunk it. I just wanted to touch on that. So the problem, the solution is called renormalization. When you essentially,
it's not the solution. It's really just an excuse, and it's as stupid as it sounds. Infinity is something, and that's it. So they developed this, and they made a couple of predictions for other relatively unimportant stuff like the anomalous magnetic moment of the electron or the Lamb shift. But if you really look at it closely, if you investigate it in the historic perspective, and that's the great piece of work Oliver Conser did, it's really a mess of tinkering, theoreticians tinkering their work towards the experiment and vice versa. So it's a mess. And just Paul Dirac, if I might quote, he said, renormalization is just not sensible mathematics. Sensible mathematics involves neglecting a quantity when it's infinitely small, not when it's infinitely great and you don't like it.
Yeah, I think that's really important. It's a huge infinity. It's not a small one. Yeah, and I think that neglecting it would really steer us away from understanding something really important, which I think, I love your idea too. That's where I was going with it too, Anastasia. But I mean, fundamentally, there is no agreement about the meaning of that as well. So, it's fascinating. I mean, I think it goes back to the idea that you can always learn something from these particularities of a formula, right? If it matches the phenomena, and there's some unexplained terms, it's your job as a scientist to make sense of what the heck those terms are telling you about the nature of the phenomena.
Yeah.
That's really interesting.
Well, you were going to lead us to the big picture just now, away from quantum electrodynamics.
Yeah, even before, as I said, quantum mechanics, as successful as it is in predicting all these spectra of hydrogen atoms and all these lines, it's really very good in this. It has fundamental problems, and such as is it a wave or is it a particle? And people were desperate. Schrödinger said, I will stop being a physicist if on Mondays, Wednesdays, and Friday it behaves like as a particle and the rest of the week as a wave. I don't like that. It drives me crazy. It's interesting. It's an interesting matter of scientific culture, how that was discussed in Europe before the World War II and in America. In America, people were saying he explicitly Heisenberg said this explicitly to an American physicist. We are desperate. What do you think about this problem? And he said, "Well, what's the problem? Let's call it wavicle. We do calculations, and it's fine." So physics has a little bit shifted from these fundamental questions to just building models with whatever number of free parameters, and if it does not fit yet, you introduce another free parameter, and that's it. That's fine.
Why are they so uninterested in the interpretive level? Why do the physicists
why do they care about CERN?
Just why are they not interested in answering the basic question, what is a particle exactly? And considering that, well, maybe it's an abstraction and not an actual body that's capable of doing these things, and that would perhaps put them on the path to reconciling this wave-particle conundrum. Why are they so interested in these fundamental interpretive steps?
Or you mean so uninterested?
Did I say interested? Yeah, uninterested. Why does physics unburden itself from these fundamental questions?
You're asking me.
Maybe you have some insight.
That's what I'm complaining all the time.
I mean, I'm complaining too. I wonder why nobody cares. I mean, if you try to write about this stuff, the physics journals will be like, this is a philosophy question. And if you could try to write about it in a philosophy journal, they're like, this is for physics. And there's no home for this discussion. That's what's really concerns me, is I don't feel like there is a discipline that is cut out to handle this question.
Sorry. Yeah. Mm-hmm.
No, hold on. I want to hear what you have to say.
No, there is a lot of fundamental questions which are swept under the rug. I mean, even Feynman. I mean, he's a representative of the modern physics, so to speak. But he admitted. I mean, the fine structure constant, for example, 137, 1/137, is some measurement value, some mysterious number nature provides us with. Where does this number come from? He says, every good theoretical physicist writes this number on his wall and worries about this. Yeah. Do you see contemporary physicists worrying about the fine structure constant? No. I mean, I admit, okay, it's very difficult. A lot of smart people fail to do any progress over decades. Okay. But as a matter of fact, it's something very fundamental, something unsolved. Okay. And we have a lot of displacement activities today. Fundamental physics is difficult. Maybe it was too difficult. Maybe it's too difficult for the human mind to resolve. But I mean, what we're doing is just skipping around and doing other stuff instead of true physics. Okay. And but let's not talk about too much about critique. What I'm proposing, maybe what could we do to get back to these fundamental questions? Mm-hmm. Historical approach. There is some progress. There are some fantastic inventions physics has done. So let's analyze how they are related to technically to progress. Mm-hmm. And I said every revolution in physics was related to a simplification, in the sense that we had less fundamental constants afterwards. It was Hertz's discovery, c² equal related to the electrical and magnetical constants. Also, Bohr's model of quantum mechanics, which is, you might call that the core of quantum mechanics, what we have found out about the atoms, is in essence a simplification, is expressing it's a little bit technical, sorry, the Rydberg's constant, which was found 30 years before by Johann Jakob Balmer, expressing it with other constants of nature. the formula is a little bit more sophisticated, but at the very end, you had, say, 5 constants of nature related by one equation. So we have eliminated one, and you have 4 independent constants afterwards. This is the huge progress of quantum mechanics. Okay. So if you take that view of physics as a long-term process of understanding and eliminating these unknowns, these gods, you explain the gods, then how far you can get theoretically. Okay, this is the question. And that's what basically I addressed in my latest book on the mathematical reality. I say that, okay, we have made some progress, some very important things, but unfortunately, there is still a couple of important constants we have not been able to calculate.
Yeah, and even from a bigger picture, it seems like the prize in the sky is being able to unify the macro scale events with the quantum level events in general. Like this unification concept is the sort of holy grail of physics, right? Being able to simplify the dynamics of the universe in terms of all scales.
Do we have a single sentence explanation of why that's so hard?
Before you're saying?
Well, no, I'm saying like right now, like why is the unification across the very big and the very small so difficult?
Well, just the unification is just not there yet, I would say. Okay, I don't know. Maybe it seems easy once we achieve it. We don't know, but we don't have it at the moment. What we have is observation of, we talked about before, the radius of the universe. That's a measurement. It's quite uncertain and it has not the best accuracy, but we're talking about 10 to the 26 meters. Okay. That's the visible universe. And we have the size of the proton, the smallest particle in the universe. Yeah, forget about the electron, which is not measurable. Let's take the proton, the other elementary particle. It has a measurable size. And now you have, you compare this size and you get a huge number. Turns out that the horizon, the radius of the universe is 10 to the 40 times bigger than the radius of the proton. And Paul Dirac related this to the relation of the electric force to the gravitational force, which is also a huge number of 40 digits, more or less. Okay. And he said, oh, this is an incredible coincidence. There should be some unknown connection between atomic physics and cosmology. And this is also one of my favorite problems I like to mention. It's an unsolved problem. It's known for almost 100 years or say 80 years, but we don't have a solution. Yeah.
What's the formal name for this problem? It's
called large number hypothesis. So he started from this relation of the electric force and the gravitational force. You said that they had the same structure, the 1/r² law, okay, but with different constants. And it turns out the electric force is incredibly stronger than the gravitational force. Yeah, I mean, just take a magnet. A magnet, the force of that little magnet in your hand overcomes the gravitational force of the entire Earth. So these are the 40 orders of magnitude. And Dirac pondered over this problem already before cosmology started. But of course, when then the first measurements of the universe came out, he said, "Oh wow! There is another occasion. There's another 10 to the 40 in nature. The relation of the horizon of the cosmological horizon to the proton." Yeah. And this is an unsolved problem. It's even more, you can say, okay, many people dismiss it, could be coincidence. Well, it can be coincidence. But there is a second, evenly stunning coincidence. If you count the number of particles in the universe, more or less you have an estimate of the mass of the universe, and you have the mass of a proton. And you have 10 to the 80 particles, which is the square of this magic number, 10 to the 40. So, and that means that the size of the size of the proton and the size of the universe and the mass of the proton, these are messages of nature we have to explain. Okay, and we haven't done it yet. So there are many fantasies, people talking about, oh, how could possibly these theories, quarks, gluon, plasma, in the very first seconds relate astrophysics to particle physics. I don't think these are the right ideas. The only smart quantitative idea, not just blah blah, the only quantitative idea is Dirac's large number hypothesis of 1938, but it's unsolved. We don't know how to build a theory around. Yeah.
Okay. Do you think that its solution will be intuitive?
The way you get to solution is probably you need a lot of good intuition. The solution has to be convincing, has to be, of course, also calculations and quantitative predictions, and so you can measure the if it's a successful theory, you need the coincidence of experiment and theory. Okay. Yeah, there is a chapter in my Einstein's Lost Key, how to possibly relate Dirac's large number also to this idea of variable speed of light. But yeah,
because it makes sense to me that if what we mean by all of the matter that exists is all of the atoms that we can see, i.e., all of the ones that we're photogravitationally connected to directly or through some relay that we can observe, then you would easily pull out the number of atoms. Well, let's say protons are all atoms are essentially composites of the proton, and
yes.
So you would. I don't know. It just seems like you're basically counting up all of the connections between all of the different atoms, and that their forces are going to be in proportion to their connectivity.
Yeah, like Shiloh and I will sometimes have this conversation where, people use the word universe. And the question is, when you say universe, is it everything or is it everything that you can detect? Because there's something that lies beyond your bubble of vision.
Well, I don't have a different take here. Just I use universe as everyone else does it. I mean, of course, everything we can observe, and we don't know what we will see tomorrow in our telescopes. Maybe some pink elephant will pop up, but it's not likely. So the universe is likely to look very, very, very similar if you observe it tomorrow.
I mean,
what's so
was that
fascinating?
your question, or
no, the question is this, where I'm like, okay, so there is some number of atoms that if we take light to be a product of connectivity between disparate objects, right?
Well, light's an interaction between.
A little problem maybe with that
Okay.
phrase. What do you mean by product of connectivity?
So what I would say is that the reason that you can see the light from Vega,
Or just from the light bulb.
or from the light bulb, I mean, for some reason I think about it cosmically, but the reason that you can see the light coming from, here, go.
Well, it's very difficult to imagine light without two atoms. One's an emitter and one's a receiver.
Is there light in a single atom universe? If you take a spherical cow?
I mean, we've been to the bottom of the well with this. People like Carver Mead have gone through quantum electrodynamics and pulled out the math that supports the idea that atoms are undergoing a conversation which is called light. Both atoms are participating in the conversation. And I don't know, what's really interesting to me about this,
Nice. Yeah, I see. Yeah. Mhm,
yeah,
mhm.
and what I wanted to say is what's really interesting is if we define the universe as everything we can see, then talking about the birth of everything we can see is a very rational concept all of a sudden. But talking about the birth of everything that exists being stuff that we can't see too, and just like the appearance of material and stuff gets into a weird supernatural realm. Go ahead, Nancy.
Okay, so the way that I see it is that imagine that there is a mixing constant of the universe, like a diffusion coefficient of how long it takes for stuff that's inside of a sun or inside of a planet to get mixed into the entire galaxy, and then how long it takes for it to get mixed in between galaxies, and how long it takes for it to get mixed out to the very edges of what we can see. What you're really getting from that is you're getting a moment in time where all of the atoms that are now scattered are part of the same body, and they're nearby and they're connected. And as they scatter and mix through the universe, you're getting this sort of almost echolocation of what is out there. But the only things that you can see are the things that have a lot of atoms shared with your origin point, however many billions of years ago, as part of the diffusion coefficient of all matter.
Okay, there are again a couple of avenues, a couple of different answers. But I tried. Maybe I'm not exactly hitting what you were saying, but what comes to my mind is that, well, a diffusion coefficient in the very narrow sense, I don't think that what would happen or will happen with diffusion, because simply we have this, not material expansion, but also no reason to form that, well, soup that is well mixed, so to speak. They will not just not come back again. But we're talking about what we observe conventionally. As I said, we have not yet figured out what's the connection between distant masses, between distant atoms that somehow must exist, because we evidently we have something like Mach's principle, or there's good evidence that this is realized in nature, but we don't know the mechanism. This instant long distance mechanism. But the other argument you touched is, and I think this is very fundamental, if you think about the interaction of light and matter, and you ask if I can imagine a universe consisting of one atom, or is there light? You can both imagine a universe without matter and just light, maybe different frequencies, but it would be very boring. I mean, light would never land anywhere and not transfer information to anyone. So, and on the other hand, you can also imagine a universe consisting only of matter, and there's no light. Maybe not boring, but everything is happening in the dark.
Very, very cold.
No one, not necessarily. It could move, but moving charges emit necessary light. So you're already hitting contradictions here. Anyway, the key question is, I think, one of the most underestimated questions in physics is why we have these two distinct phenomenologies, light and matter. Why light with this property, and why matter with this? We're so used to it. That's part of our everyday life and everyday life of physicists and observers, but it's still a fundamental question. Why we have matter and light?
Yeah, I think Carver's really onto something with light being a activity and matter being a material that has a surface and body. Matter? What?
It's the actor.
Yeah, it's the actor. One is the actor and another one is an action. And so if you start treating an action like a body, you run into all sorts of confusion. But
I also think that the question of why is there light and why is there matter is the same level of question of why is there a hurricane, why is there a tornado?
Well, it's like, why is there a hurricane, and then why are there water molecules in the hurricane? Or something?
Kind of, it's almost like a question of organization. I think about this, and this sounds so weirdly mystical, but I feel like there are shapes that the universe likes to make, and that's so personifying the universe. And I think that it's probably a product of, the shapes that water makes are a product of the geometry of the water molecules. The shape that the universe makes is a product of the stuff that makes up the universe. And the matter is the actor, the light is the action, but the basement of their creation is like almost an identity property. Like if you we were having this really cool conversation with a guy from the Quantum Bicycle Society, John Williamson, and he used the concept of the stuff to describe this. It's the foundational goo that everything is made of, and it has some kind of physical property, and so it aligns itself in these shapes because they're the
shapes are the motion of the material, yeah, essentially. Just like the shape of a tornado is the motion of the air molecules.
Yeah, like in a fractal way, like there have to be bonding angles, and there have to be velocities, and there have to be frictions, and all these material properties that we see on the what is it, the supra-atomic scale?
Yeah, it seems like solving these questions really comes down to having a really solid structure for the atom, including whatever it is that's connecting atoms to one another, which I would hypothesize is made out of the same stuff as the atoms themselves. And so solving those questions will illuminate the answers to all of these other questions, I feel like.
Yeah, we agree that it's an unsolved problem. And there is the best strategy is, allow any kind of ideas, and everyone should be allowed to pursue very crazy sounding ideas off the mainstream, and just allow that, and then get back somehow to observations and link to that. And my take would be on the light and matter question. That I like the constants discussion, and I think constants are important, and we need to explain them. And there is a relation of light and matter to constants. Light is obviously related to the speed of light. This is a constant. And matter is related to Planck's constant, H. Okay? And if you want to, this would be the corresponding two quantities to the concept of light and matter. Instead of explaining why light and matter, try to explain why nature needs this speed of light and why nature needs this quantum of action, which is an unsolved problem. These are, again, two gods of modernity. We believe in these two gods and constants, and we don't question it anymore. We don't ask ourselves why physics has necessarily this speed of light or has this quantum of action. Could there be laws of physics doing without that? Or would the world be better off without these two constants? But we must answer these questions. And I think once we can explain C and H from first principle, we will be very closer to the question, what is light and what is matter?
Yeah, and what's interesting is that if indeed C is not a constant, then what other constants are not constant?
Okay, you're very good in correcting me, because it seems contradictory if I don't explain this. I am talking always about a variable speed of light, and that's also a reasonable concept. But even if there is a variability in space and time, you have this constancy of the speed of light of Einstein's special relativity, constancy with respect to an observer. Okay, if you are today in one point, the speed of light does not change whether you are in motion or if you are in rest. Okay, this is the constancy of the speed of light, the famous constancy. Einstein developed his first special relativity theory. Okay, so we have this, let's say, the phenomenon of this speed of light, and you can imagine this as a strange speed limit. Why can't you accelerate masses beyond the speed of light? Okay, in Newtonian mechanics, this is very, there is no reason whatsoever for that. Just accelerate. Okay. Why do you have this speed limit? There must be a reason for it.
Well, in all other substances, the speed limit of deformation is specified by the material architecture, the subunits, and how it's arranged at the subunit level. So it makes sense to me that the medium that's conducting light would also have a speed limit, just like any other material that is the product of its architecture.
Okay, I'm a big fan of this ether theories of electrodynamics, and then you would distinguish between longitudinal and transverse speed of light, and indeed you can describe light as transverse. There's a lot of analogies between the transverse speed of light and the speed of sound, sorry, and the speed of light. But I mean,
it's a helical wave. It's a helical wave.
To postulate another level of stuff, okay, which is beyond. So if you want to understand from first principles, I would say, a couple of other questions would follow. So, what is this ether or stuff, or you observe the lights? Why has it a certain rigidity? I mean, you can say, okay, I have explained the speed of light, but at the same time, the speed of light depends on the density and on the elasticity. So,
yes,
instead of asking where does the speed of light comes from, you have to ask where does the elasticity come from? Okay.
Yeah. I mean, I try to avoid the word ether because it gives the idea that there's a separate substance from the atoms. But what we're proposing is more just that interconnecting material is just an extension of the shells themselves. It's of the same fiber as the atom itself. So the tensile property.
Exactly. Wonderful. I fully agree. Yeah. That's why.
And that last question where you say that first you go from why the speed of light, then you go to why the material properties, is touching on Gödel's incompleteness theorem, which is that you can't possibly answer all questions within a theory. At some point, you have to start with the axiom of like, well, this is the floor. Beyond this, the theory cannot explain. And then you ask a different question.
I guess you caught a little bit of my ignorance here.
I mean, all she's saying is that there's a boundary condition for a statement, right? If you make a theory, you have to bound it at some point. And then you have like a different theory to explain. Like you can't explain everything all at once. You just
like if you explain all the physical rules of the universe, you haven't explained why there is a universe. That's a different question. That starts from different.
I can live with that.
But like
I would die happily.
Right? But somebody might come along and be like, "Well, you haven't explained why there is a universe," and they would technically be correct, right?
Yeah, I have to think about the Gödel, but I'm risking to say stupid things. So I would rather. Well, I would say. Well, if we are very ambitious, then let's take that philosophical point of view of Einstein. And he said, I don't like numbers which the whim of the creator might have created in another way. So he wants explanations. And let's try to explain all the constants of nature, which is a lot of difficult fundamental things to solve. I mean, I guess it would be 6-7 steps, revolutions still ahead of us until we arrive in explaining the very last, the most important constants of physics. I think in theory, this could be feasible by super intelligence or computers or whatever. But the real problem is in explaining C and H, because there is no explanation why these constants are there, and that means, in my opinion, something is wrong even before something is wrong with our idea of space and time. That might be the misconception which has got us into all that trouble.
But if the speed of light is, so you said that it's locally constant and not in the way that we've been talking about it, is that it's not constant over these great distances. That means that there is something local.
As it interacts with matter.
As it interacts with matter, right? So but can you fake that locally? Shiloh, this is a question to you.
Oh, I'm sorry. Can I fake that locally? So,
can you approximate the same matter-light interaction shift that happens across 13.4 billion light years on Earth inside of a laboratory?
I mean, that's a great question. Yeah, is there any way to demonstrate the variable speed of light in a laboratory? Can you imagine an experiment?
You have the problem of the corresponding variability of wavelength and frequency of your laser. Yeah, so you have to look at this variable speed of light more in another way of interpretation of cosmology and the results. It's not that there is an easy experimentum crucis, an experiment that decides whether it's correct or not. It's not that easy.
Do you know Dowdy's work about the variables, about the refractive index, and
what's the name?
It's Edward Dowdy, I believe, is his name. I might get his first name wrong. He worked at NASA for a while, and he wrote a few.
Think so, no? Yeah.
Okay, yeah, he's pretty interesting. He's got he did a video with Pierre, actually. He came and stayed at Pierre's house and did a pretty interesting video, and he wrote a couple of papers. He worked at NASA for a while in a bunch of different places. And he was basically saying that the gases in interstellar space, particularly the ones surrounding stars, would be capable of this achromatic refraction in the same way that gravity would. And he did some mathematical proof for how it would be congruent with gravitational processes that had nothing really to do with gravity, but had everything to do with the composition of the stars that were refracting the light, or lensing the light, I guess is the proper term. And he brings up a couple of really interesting points, like one of them being that we don't see these Einstein ring things all the time. We only see them in a few galaxies. And if it was the case that light was actually being bent by mass, then why would we not see little halos around every star in the sky, something like that? I don't know if that's something you thought about.
I can't really comment a lot. Could be interesting. I mean, well, regarding the gravitational deflection of light, I mean, there are people claiming that this is not an effect of gravity in the first place, but
I think that Dowdy's
classical effect of an atmosphere. And it's funny that, I mean, if you follow the ideas of Marie Robitaille about the sun, the consequence would be that the sun's atmosphere would have to be much denser, so maybe the effect would have to be more pronounced. So maybe there is some value in this. Still, I don't, let's say, in that sense, I believe the classical interpretation that indeed the Eddington's measurement of 1.75 arcsecond is a gravitational effect and not an artifact of.
Yeah, he attacks that too. I wish I could recall.
I'm looking at Dowdy's Beyond Mainstream website right now. So thank you, David DeHilster. But it basically, to summarize it, is that gravitational lensing is not observed outside the corona of the sun.
Yeah, that was the main thing I wanted to bring up.
And because if it's not observed outside the corona of the sun, you wouldn't expect gravitation to stop at the corona of the sun. And so if it's gravitational, you would expect that it would fall off with distance from the sun. But once you're outside of the corona, you no longer see lensing. Again, I don't know if that's accurate or not. Guy
Yeah,
was
unfortunately, he passed
I could
away.
be mistaken. I could be mistaken. Maybe I misunderstand something, but I think gravitational lensing is pretty much observed everywhere. I mean, you don't look at the sun if you want to.
It's not that it's not observed everywhere. It's that if you were to look at the sun and see what was lensed, the things that are lensed are only the things that are within the corona, nothing that goes beyond the corona.
Okay.
And again, I don't know if this is accurate or not.
I wish so badly we could have him on the show, but he passed away recently, unfortunately.
Yeah.
Because he's the only person who's really made any convincing argument. And I'm not a good enough mathematician yet to tear it apart. I'm working on that.
We have big plans.
Okay,
We're going to take a
maybe we
math
should
class next
talk about that in the future.
Yeah.
We'll send you a link when we get offline. I have a totally out of left field question.
Please.
Quantum computers. Do you know anything about them?
Not really substantial, like.
Okay.
There is a slight. I mean, there is a slight connection that, in the sense that what I consider interesting as an alternative model for space and time, which are quaternions, and quaternions are could be a very useful tool to describe the quantum states, and in turn also be useful in quantum computing. Yeah, but that's, I mean, a little bit far-fetched. I'm not. I cannot. I don't think I can say anything reasonable about quantum computing and the prospects. I'm not just not in that business.
I think that the reason that I ask is because I feel like that's one of those places where quantum theory and quantum electrodynamics would be at the applied phase. And from everything that I've read, there's significant problems with the theoretical underpinnings of quantum computers that's preventing them from being able to build an effective system. And so that was the reason that I want to know more about it, is because I know very, very little. And so I'm hoping to find somebody who can relate the theoretical concepts to the physical thing that's being built, and then elaborate on the issues with it. But I don't.
Well, yeah, it'll be the proof is in the pudding kind of thing.
I don't think the quantum computing has anything to do with quantum electrodynamics. I mean, quantum electrodynamics, I think, is completely useful and will turn out as such. I don't think it will be useful for quantum computing either. You're right that, quantum computing would be a very nice application of quantum mechanics, if you want. And if there are some basic flaws or problems, they could possibly also pop up in that field. Yeah, I know someone, a mathematician from Ireland, who has published about the unit quaternions, saying that there will be problems with quantum computers, but I can't tell you from my own knowledge if this is sound or not.
That's fine. I didn't mean to put you on the spot. I was just hoping that someone could help me.
Have you published on the Quaternion idea already?
I have just published that book about the mathematical reality, and I have published a book about the origin of constants C and H, and I'm relating this to quaternions. I think that if we want to arrive at the proper understanding of these two constants, they might arrive from non-commutativity of quaternions and from a tangent space, which are both properties of this mathematical object. There's a little paper, but it's short and speculative. It's a very first approaches, so to speak. I cannot claim I have a theory in that sense. I see this. I see this more as a question of method. Yeah, as I said, start with constants. Think about constants. It's not possible that we have these gods of modernity, and if you go ahead with explaining, you're sooner or later arrive at either quaternions or maybe another mathematical object that is interesting enough to replace the conventional space-time. But probably we need an alternative here.
Have you read much about this amplitude-hedron idea?
What idea?
It's called the amplituhedron. I'm gonna mess this up. Somebody's gonna be pissed off. Amplituhedron.
Yeah.
I guess this is
No.
another proposed alternative to
No.
space-time.
It's like it's beyond space time. Again, this is something
Yeah.
that's like beyond my level of understanding.
Yeah, our friend Don Hoffman brings this up all the time.
Yeah.
It's gonna save space-time.
You guys are doing a great job in the sense that there are a lot of interesting alternative ideas out there. And I think the interesting thing is here that, I mean, obviously there is a lot of doubt about the standard models, a lot of gut feeling of many researchers that say, no, that cannot be, that 26 parameters, that's not, aliens would pay us respect for having found out, having developed such a model. There must be something wrong. And I think that gut feeling is really, really widespread. The unfortunate thing is that we heterodox alternative guys, we usually disagree with each other. We don't form big organizations fighting against the standard model because it's in the very nature of these trials that these ideas are also different. And so I'm a little bit ignorant about maybe some other interesting idea. And
Well, best case scenario, you guys come up with the same idea and give it different names, right? That happens. Yeah, that happens, right? I mean, different people come up with calculus.
Yeah, but that's again where I prefer history. But as a matter of fact, you have lots of guys. I get every week 3 emails about an explanation of the fine structure constant. But if you go to history, that is stuff that is valid over the times. It's just like comparing contemporary music to Beethoven or Mozart. Well, okay, that's some quality that is you can still believe. And if I read an old paper of Schrödinger or Dirac and say, okay, this is an interesting idea, then I try to build on that. Yeah. But maybe I miss also something very interesting of the present. Could be. Yeah.
And there's a lot to think about. I think it's been a fantastic conversation, and we could easily put a pin in it here and then open it back up again in a little while. Because I know you're constantly working. Like, what are you working on right now?
Yeah, a lot of stuff to do. I try to organize my time. I'm currently working on a book on the sun, basically Pierre-Marie Robitaille's model of the sun. And I hope to complete this, and then hopefully I will get back to thinking about the fine structure constant, as Feynman said. But it's the difficult problems are frustrating, and at the same time, so you have to work at different problems, and
maybe studying the sun will give you some insight into the other more fundamental processes too.
Yeah.
That's definitely.
I really am looking forward to that book.
Of course, I will get back to the unique Quaternions, but it's kind of that I need a little bit help of mathematicians. I feel that because I'm a physicist, I'm thinking intuitively, and calculations or mathematical abstraction is not really my best quality.
So any mathematicians,
math collaborators would not be bad. Yeah.
Yeah, any mathematicians listening, there's an open position.
You need a Minkowski is what you need a partner out there.
We need a Minkowski as well. We need I think that the
Well, the wrong one. It could happen that the wrong person arrived. I guess that Minkowski or Grossman was a disaster for Einstein. He would have better developed.
Interesting.
Okay. A mathematician, but a good one, the right one, not the wrong
that makes
one.
me feel better then.
Yeah, open call. Any mathematicians listening, please reach out. I think that would be good.
Okay.
Yeah.
Well, it's been really fun to talk to you. Yeah.
It's been fantastic.
I would love to.
Anastasia, for you. Yeah, it's really great, this podcast.
Yeah, and I'm gonna go think about some of these constants, and maybe we can meet up after I have some better ideas going on.
Okay.
All right. Thank you, Dr. Unzicker.
Thank you.
Yeah.
All right. Have a great rest of your night.
Goodbye.